Flack math! Give me some math and I'll give you some flack. Flack math!
All right, 21, we're going to talk about prime and composite numbers. Okay, have you guys heard that word composite before in other situations in life? Where have you heard that? Evie?
Composite bats for softball.
Composite bat. So what is a composite bat?
It's made out of carbon fiber.
It's made out of carbon fiber and other metals, not just carbon fiber, but other metals. So what happens is that there's multiple ingredients into that. Like composite wood. Do you know what composite wood is? You can either buy like pure plywood or you can buy composite wood. So that's different kinds of wood that are in one sheet of plywood. Okay. A composition. What's a composition?
It's a notebook.
It's a notebook, composition notebook where you put a bunch of notes in there, right? A composition in music is like a song that has a bunch of parts to that song, right? So a composite number has a bunch of parts in that number. So it has a lot of stuff that goes into that number. So what's an example of a composite number? Kiara? 10. Because what goes into 10? Well, 1, 10, 2, and 5 go into 10, right? Those are all the numbers that go into 10. What's an example of a number that's not a composite number? Yeah.
7.
7. The only thing that goes into 7 is 7. So you can't take it apart into separate parts. The whole thing is it's one part. Anybody ever take apart an engine?
My dad has.
Yeah, so it's kind of cool because you try to take it all apart until you can't take the parts apart anymore. So those are like the prime parts of an engine. Like there's no screw that you can undo something here or no bolt that holds it together. It's done. That part was made for that purpose. Okay? So that's a prime number. All right? A prime part. You can't take it apart anymore. Yes. Uh-huh. Okay, so if you think about all the counting numbers, what are the counting numbers again? 1, numbers you count with, right? 1, 2, 3, 4, 5, all the way up to infinity, right? Those are counting numbers. So all counting numbers are either what we call prime, which means you can't take it apart, or composite. I'm not talking about fractions or decimals or anything like that. I'm just talking about counting numbers. Okay? So let's think about prime numbers. Can you list prime numbers? So what are some examples of prime numbers?
11.
11 is a prime number. Okay? So here's what I'm going to do. I'm going to just list like a bunch of numbers and then we'll just start. It's probably easier to talk about numbers that aren't prime than to talk about numbers that are prime. Well, maybe not. But let's just eliminate the ones that are prime. So here's 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. We'll stop there. Okay? So let's just start getting rid of the numbers that we know are not prime. So composite numbers. What are the really juicy composite numbers? Hunter?
1, 2, and 3.
So 1, 2, and 3 are not composite numbers. But first of all, 1's not a prime number either. I'm talking about composite numbers, numbers that you can take apart.
I thought you said we were getting rid of all the prime numbers.
Yeah, we're eliminating all the composite numbers. No, that's what I said. Okay, so what are the obvious ones that you can think of, the composite numbers, the nice juicy ones that you can take apart? Yes?
20.
20. And really, all these guys, right? So we know that those are all even numbers, right? And 2 goes into all these. 2 goes into all these. Look. So I can get rid of all those. I can get rid of all these. I can get rid of all these. But what can't I get rid of? I can't get rid of 2. That's the only even number that I can't get rid of.
Why not?
Because what are the factors of 2?
2 and 1.
Just so nothing goes into 2.
Oh.
Except 2 itself and 1, right? And that's not really breaking it up into parts. The only factors are 1 in itself. That doesn't really divide out any parts, okay? So 2 is the only even number that's prime. What about 3? Is 3 prime? Yes, the only factors that go into 3 are 1 and 3. What about 5?
Yes.
Okay, but how do you know if a number is a multiple of 5? If 5 goes into a number? Marin?
If it ends with a 5.
Ends with a 5 or 0. We already eliminated all the zeros, but look, we can eliminate all these 5s. So we don't even have to check those odd numbers. Okay, what about 7?
Those are all prime.
7 is prime, but these aren't necessarily prime. Can you see a number in there that's not prime? So remember, a multiple of 7 is not like it ends in 7. Yes, Avery?
27.
Yeah, 27 is a multiple of 3. 3 times 9 is 27. So you can go through and find your other multiples, or you can, from here, really we're just checking for multiples of 3 and 7. Because multiples of 6 are all even. I don't even have to check those, right? Because even numbers are not prime. But 9, is 9 prime? No, because 3 you can divide it into 3 parts, okay? What about 11? We already said that 11 was. What about 13? 13 is. What about 17? 17 prime or not prime? Prime. What about 19? Yeah, so the lower numbers are easy to point out if they're prime or not, because we kind of know our multiplication chart. What about 21? 21? No, it's not prime. What goes into 21? 7 and 3. What about 23?
Not prime. Yeah, prime.
Prime. Nothing goes into 23. What about 27? We already said that 3 and 9 go into 27. What about 29? You have to think a little bit, don't you? Is it prime? Hunter says thumbs up.
It is prime.
Yes, it is prime. All right, what about 31?
Prime. No.
Prime. What about 33? No, what goes into that? 3 and 11, right? If it's the double digit of the same digit, then 11 goes into it. What about 37?
Prime.
What about 39?
Not prime.
Not prime. Good catch. 39 is a tough one to catch. What goes into 39? 3 does how many times?
13.
13. So 39 is not prime. So you're going to be tested on this. You might be asked to find the prime numbers between 30 and 50. You can do that, right? So you don't have to check the even numbers. So you can skip all the even numbers. So just check all the numbers that aren't even and maybe not all the multiples of 5. So you're going to check 31, 33, 37, 39. Then check 41, 43, 47, and 49. You only have to check 8 numbers to see if they're prime or not. Can you do that? Okay, good. Yes?
Is 49 a prime number?
It's not, but that's just where you can check. So you know you don't have to check the even numbers, right? And you don't have to check the numbers that end in 5, because those are multiples of 5. And then you just have to check for basically multiples of 3s and 7s, and 49 is a multiple of 7. So you're only checking 8 to see if they're prime. I'm not saying that those 8 numbers are prime. You're just checking. You don't have to check every single number to see if it's prime, because you can eliminate all the even numbers and all the multiples of 5. So you're really just checking numbers that end in 1, 3, 7, and 9 in between certain numbers. Yes?
What about negative numbers?
Good question. So prime and composite only applies to counting numbers bigger than 1. Okay? So a prime number is any counting number greater than 1 that only has 2 factors, 1 and itself. Good? All right. Okay, so this is fun. You guys remember doing factor trees?
They're definitely not fun.
I love them. I love factor trees. So basically a factor tree, you can make a factor tree. You're basically trying to figure out what prime numbers you have to multiply together to get another number. So any number, any composite number, or any number can be written as a product of prime numbers. So for example, 14, you can take apart that engine. What times what equals 14? Yeah.
7 times 2.
7 times 2. And then can you take apart 7? No. Can you take apart 2?
Yes.
So the product of primes that equals 14 is 7 times 2. That's it. Okay? Some of these you can do in your head, but some of these you might need to map it out, like with a factor tree. There's 2 different methods I'm going to show you on how to do this. But before that, let's put this definition down. Counting numbers greater than 1 with only 2 factors, 1 and itself. Okay, so you can't take it apart. Composite number, you can. You have composite numbers have 3 or more factors, right? What's an example of a composite number that has 3? Wait, where did I get 3? Yeah. 10 has 1, 2, 3, 4 factors. 1 times 1, 10, 2, and 5. What's an example of a number that only has 3 factors?
3.
Yes, Addie.
9.
9. 1 times 9 and 3 times 3. So you don't have to say 3 twice. So the factors of 9 are 1, 3, and 9. Or any square. Do you know what a square is? Not the shape, but a square number is anything that you can take the square root of. Do you remember talking about square roots? The square root, what times itself equals 9? 3. What's another square? What's an example of a perfect square number? Something that's square rootable.
15.
Not 15.
6.
16. Because 4 times itself equals 16. So now 16 has 1, 2, 3, 4, 5 factors. 1, 16, 2, 8, and 4. Right? So you don't have to say 4 twice. Yes?
What about the square root of 2?
Square root of 2, 2 is not square rootable. The square root of 2 is actually what we call an irrational number. It's like 1 point something. And the decimal is really ugly because it goes on forever and it doesn't repeat. It's kind of like pi. You know, the decimal of pi goes on forever. Pi is another example of an irrational number. So don't you hate it when that happens? Yeah. All right. So let me put some numbers on the board. Composite numbers, let's define this. Divisible by a number other than 1 in itself.
One office to 2, please.
Holy. 3 or more factors. Just write that down for composite numbers. That'll work. All right. So every composite number, all the ones that we just crossed out, can be written as a product of primes. Give me a number between 1 and 1,000.
2. 17.
2 is not a composite number. 17 is not a composite number.
50.
528. 528 can be written as a product of primes. Okay? Let's try that. 528. What times what? I know it's not a composite. How do you know right away that it's a composite number?
It's even.
Yeah, so 2 goes into it, right? So let's take 2 out. Can you do that in your head? Let's see. 2 goes into 5 2 times. How many? 264. Is that right?
No, that's definitely not right.
It's not right. I think it's right.
Nope, it's right. Nope, it's right.
264 times 2, right? Well, 2 is a prime number. So I'm going to circle it. So if this is a tree, it could be like a cherry tree. And that stops, so there's no more branches coming out of 2. But there's branches coming out of 264. I know right away that that's composite because it's even. So guess what? 2 goes into that. How many times? Well, let's see, 132. I know right away that that's prime, right? So how many times does 2 go into 132? Can you do that in your head? 66. I know right away that that's prime because that's even, right? How many times does 2 go into 66? 33. Now 2 doesn't go into 33, but what goes into 33? Hunter? 3 times what?
11.
3 times 11. So look at this. This is my product of primes. Let's see, I've got 2 times another 2 times another 2 times another 2 times another 3 times 11. That is 528. I just took apart the engine of 528, and that's what it looks like, all on the garage floor. Okay? How would you check to make sure this is right?
Multiply that.
Yeah, just multiply it. Do the math. All right? Well, this is 2 times 2 times 2 times 2. That's 16 times 3 is 48 times 11. 48 times 11 is 528. That works.
Did you just say that, or did you actually do the math?
Do you know how to multiply a number by 11?
You
two
just add the number, and then you just do like 2 times
So,
11 is 22.
Multiplying a single digit times 11 is easy, right? 7 times 11 is 77. But a 2-digit number like 27, what did you say, Grady? Do you know how to multiply times 11? The shortcut, do you know, Kiara?
No, yeah. So you multiply the number times 10.
You could do that and then
And
just
then
add one
yeah.
more. There's an easier way. It's a shortcut. It's really cool. All the cool kids are doing it.
Just multiply.
Hunter, do you know?
Use your brain.
Use your brain. Yes.
Wait, do you
Okay, here's how you multiply by 11. You would separate the 2 and the 7. Oh no, I want to be together. And then you add them together. What's 2 plus 7? 9. So the answer is 297. Give me another 2-digit number.
47.
47. Now, what happens if when you separate them and you add them together, you get an 11? 4 plus 7, well, you carry the 1 and make it a 5. So 517. Give me another 2-digit number. Yes.
79.
79. So it'd be 7, 9, and then 16 in the middle, right? Because 7 plus 9 is 16. Carry the 1, so 869. Isn't that cool? That's a pretty cool trick. Do you have enough? So this is how you do this. There's another way to do to find prime factors. Give me a 3-digit number. Hunter?
793.
793. Well, let's see. Oh, 793.
You said 793.
I said 793.
You said 793.
You call me a liar?
Yes.
I don't know. Is 793 prime?
No.
It seems pretty prime.
No.
I think it might be prime. Give me another number.
You're wrong.
Yes.
942.
942. Okay, now instead of doing the factor tree, you can do the factor tree method, but I'm going to do 942, and I'm going to just start dividing and going up. Do you remember the shortcut to dividing? So if I take 2 out of it, how many times does 2 go into 9?
3 times. No, 4.
So 4 times, and how much is left over when you put it in 4 times? So remember, instead of subtracting and bringing down, I'm going to bring the remainder up to that 4. Okay? So how many times does 2 go into 14? 7 times. And then no remainder, so how many times does 2 go into 2? 1. All right. So next one. So 2 doesn't go into that. You want to see if 3 goes into it? Yeah, let's see if 3 goes into it. Can anyone tell me right away if 3 goes into it? How do you know if it does, Grace?
Because it's odd number.
Not necessarily. 7's an odd number. 3 doesn't go into 7. What's the shortcut, Hunter?
It adds up to 3.
Yeah, so 4 plus 7 is 11 plus 1 is 12. So 3 goes into 12, so it goes into 471, which doesn't seem like it does, because that looks like kind of an ugly number. So 3 goes into 4 one time with 1 left over. 3 goes into 17 5 times with 2 left over. 3 goes into 21 7 times. All right? What about 157? Does anything go into 157? I don't think so. That's an ugly one. So, so basically, that's it. So you got 2 times 3 times 157. Okay? This is basically factoring a number. Factoring a number is taking it apart, looking at all its factors and taking those factors apart, all the way down to where you can't take it apart anymore. That's breaking it up into prime numbers. Okay? All right, let's see if you guys can do this. Do this on your paper. Factor 420. So I want you to factor 420. So I want you to write 420 as a product of primes.
Do we write down factors?
I want you to write it as a product of primes.
What's a product of prime exactly?
What's a product?
I don't know.
When you multiply stuff together, what's a prime number?
I don't know prime number.
So what prime numbers multiplied together will equal 420? Aaron, do you have an answer already?
Yeah, is it 2, 3, and 5?
2, 2, and 35?
No, 3 and 5.
2, 2, 3, and 5?
Wait, so we're supposed
You're
to
missing
factor
one
420?
factor. Yep, factor 420.
Is it,
Yes.
is it 215?
No. 215 is not a prime number.
So what times itself? Wait, 200.
So what prime numbers do you multiply together to get 420?
2 times 2 times 5 times 3 times 7.
That's it. Okay? So how did we get that? Maren, what did you do?
I did 420. Peter. This is what I do. And then 15 times 2.
15 times 2? Oh, you got 30 times 7, right? That's probably where you got the 15, and then this is 15 times 2. 15 is 3 times 5. See why it's nice to just circle. Once you get to a prime number, just circle it. 2 is a prime number, 3 and 5 are the prime number. So now it doesn't matter how you do it, you will always end up with the same combination. Now let's write it in order. 2 times 2 times 3 times 5 times 7. But you could have done it like this. 60 goes in 7 times. 60 times 7 is 420, right? And what's 60? It could be like 15 times 4. Well, 15 is 3 times 5, and 4 is 2 times 2. Look, 2 times 2 times 3 times 5 times 7. So it doesn't matter what order you do it in, you will always end up with the same engine parts on the garage floor. Okay? Put them in order, and then multiply it to check it. Okay? Can you guys handle this? You don't have to do factor tree. I just like going down. I don't like going up. It makes me uncomfortable, and I don't know how much room I need to make for myself. But that other way, it was called the cake method, because it looks like a cake. Because you keep building layers of the cake with division symbols. Okay?
What?
Yeah. All right. Let's do the next lesson.
Black math, give me some math and I'll give you